let's say we have some ammonia gas. That's NH3, and it's a gas. That's why the G is in parentheses. And we combine that with some oxygen, molecular oxygen. It's also a gas. And that reaction produces some nitrogen monoxide, NO, monoxide. There's only one oxygen there. That's also a gas. This is also called nitric oxide, not to be confused with nitrous oxide, which is, all right, nitrous oxide is N2O. This is laughing gas. But anyway, I don't want to divert you too much. We have to focus on the problem. So this is nitric oxide, or nitrogen monoxide. It's a pollutant. I think it comes out of some cigarette smokes. I think it's used in the body as well. You could look it up on the internet. Nitric oxide. Ammonia is an important fertilizer. You know all about oxygen. And this also yields some water. So plus some H2O. And we're told that we're given 34 grams of ammonia. This is the ammonia right there. So 34 grams of ammonia. And we're given 32 grams of oxygen. 32 grams of oxygen. And this is going to be the oxygen molecule, O2. So the question is how many grams of nitrogen monoxide, or the nitric oxide, are going to be produced? So how much of the NO, just the NO, is going to be produced in grams, NO? So this is a stoichiometry problem. And so the important thing first is to just make sure we have a balanced equation before we even start anything. And lo and behold, we don't have a balanced equation. Let's confirm that it's not balanced. So let's see, we have one nitrogen here. We have one nitrogen there. That looks balanced so far. We have 3 hydrogens here. And remember, the pattern is start with the complicated stuff, leave the single atom molecules for last, because those you can fix at the end without messing anything else up. Hydrogen, we have 3 hydrogens on the left-hand side. On the right-hand side, we have 2 hydrogens. We have 2 hydrogens. So let's see. How can we have 3 hydrogens on the right-hand side? If we multiply this times 1.5, see, 1.5. Now we have 3 hydrogens on this side. 1.5 times 2, we have 3 hydrogens on the right-hand side. Things are looking good. Okay, now on the right-hand side, how many? See, we have 2 oxygens on the left-hand side. We have 2 here. How many oxygens do we have on the right-hand side? We have 1 oxygen here. And then you have 1 oxygen in this molecule, but we have a 1.5 of the whole molecule. So we have 1.5 oxygens, and then we have 1 more oxygen. So we have 2.5 oxygens on the right-hand side. And we only have 2 in this molecule. So what do we have to do? How can we get 2.5 oxygens here? Well, if we multiply it by 5/4, or 1.25, right? 5/4. 5/4 times 2 is 5/2, which is 2.5. So now, right, we have 2.5 oxygens. 5/4 times 2 is 2.5. 1 plus 1.5 is also 2.5. So now we've balanced our, well, we're not balanced yet. We can't leave this equation with just these weird decimal numbers over there. So let's rewrite it. Let's multiply the entire equation by, if we wanted to get rid of all of these, we can multiply the entire equation by 2. No, not 2. We don't want to multiply it. We have to multiply the entire equation by 4 to get rid of this 4 in the denominator. So if we multiply the entire equation by 4, we have, let me do it down here. We have 4 molecules of ammonia. Or we could even think of it in terms of moles. Right now I'm thinking of individual molecules. We could say, oh, we have 4 moles of ammonia. 4 times 6 times 10 to the 23 molecules of ammonia. Either way, it all works out. Hopefully you're starting to see the value of moles. Plus 5 molecules of, I'll just think of it in terms of individual molecules for now. Plus 5 molecules of molecular oxygen. And remember, we're thinking of things in terms of, actually, I forgot what I was going to say. And we're just multiplying everything by 4. That's what we were doing. Yields, it's late in the day, 4 moles of ammonia of nitrogen monoxide. So 4 NO plus, we multiplied both sides by 4, so plus 6 waters, 6 H2O. So there you go. We got some good practice balancing equations. So let's go back to the original problem. We're given 34 grams of ammonia. 34 grams of this. So what we need to figure out is how many moles of ammonia were we given? So what's the atomic mass of ammonia? Or not the atomic mass, what's the molecular mass of ammonia? Nitrogen, let's say we're dealing with nitrogen 14, so it has a mass number of 14. Oxygen has a, or we're dealing with nitrogen. Hydrogen has a mass number of 1. So each nitrogen has a mass of 14. And then the hydrogens each have a mass of 1. Remember, a hydrogen is kind of strange. It doesn't have neutrons, or at least in its most traditional form. So it has just a mass number of 1. It's just a proton and an electron if it's neutral. So this is 3 times 1. Right? We have 3 hydrogen atoms. So the mass, the atomic mass of one molecule of ammonia is 14 plus 3 is 17 atomic mass units. Or another way to write that, if one molecule of ammonia is 17 atomic mass units, then one mole of ammonia is how many grams? It's going to be 17 grams. 17 grams. So how many moles of ammonia are we given? We're given 34 grams of ammonia. 1 mole is 17 grams. So we're given 2 moles, right? 34 is 2 times 17. So this is 2 moles. We're given 2 moles of ammonia. Let's see how much oxygen we're given, or how much of the molecular oxygen we've been given in this case. So let's see. The mass of just oxygen by itself is 16, right? The mass of just oxygen, just the atomic oxygen. It's careful. You have to be a little bit careful here, because sometimes people say, "Oh, we have 32 grams of oxygen," where they're really talking about the molecular oxygen, right? Well, I guess it doesn't matter either way, but sometimes when they talk about oxygen, you have to make sure whether it's molecular or atomic oxygen. But the atomic mass number of oxygen is 16. We can confirm that looking at the periodic table down here. 16. So what's the molecular mass of the diatomic molecule O2? Well, it has 2 oxygens, so it's going to be 2 times 16. It equals 32 atomic mass units. One molecule of O2 is 32 atomic mass units, or 1 mole of O2 is how many grams? Well, if one molecule is 32 atomic mass units, then 6 times 10 to the 23 of that molecule are going to be that many grams. 32 grams. So how many moles of oxygen have we been given? We've been given exactly 32 grams of oxygen, which is exactly 1 mole. So we've been given 34 grams of ammonia, which is 2 moles. So let me write that in a nice, vibrant color. So we've been given 2 moles of NH3 of ammonia, and we've been given 1 mole of the oxygen molecule. Now, when we look at this reaction, for every 4 moles of ammonia, we need 5 moles of oxygen. Or for every 5 moles of oxygen, we need 4 moles of ammonia. So something doesn't gel here. Normally we need more moles of oxygen than we have ammonia. In the example that we're working through, we've been given less moles of oxygen than ammonia. We've been given less oxygen than we need for all of this ammonia, right? In an ideal world, if we had 2 moles of ammonia, we would need 2.5 moles of oxygen, right? The ratio of ammonia to oxygen, let me write that down. The ratio in a different color, this is getting boring. The ratio of ammonia, NH3, to oxygen in our balanced equation, let me put that in the square so you know this is the most important part of what I'm writing. The ratio in this reaction is 4 to 5, right? So if I'm given 2 moles of ammonia, if I'm given 2 moles of this, so this is equal to what? If I'm given 2 moles of ammonia, how many moles of oxygen do I need? I need 2.5 moles of oxygen, right? Whatever this is that right? You have 4/5, right? 1.25, right? Right. If you doubled both of these numbers, you get 4 over 5. Right? So I need 2.5 moles. But I don't have 2.5 moles of oxygen. I only have 1 mole of oxygen. So oxygen is going to be the limiting reagent in this reaction. Limiting reagent. I don't have enough oxygen. I have plenty of ammonia, but I don't have enough oxygen to react with it. So this is the limiting reagent. Limiting reagent. And I said before, you can just, the word reagent and reactant, they're used interchangeably. But when people talk about the limiting ones, they tend to call it the reagent. So oxygen is a limiting reagent. So we have extra ammonia. So given that we have 1 mole of oxygen, how many moles of ammonia can I react with that? How many moles of ammonia can I react with that? So this reaction is going to look something like this. I only have 1 mole of oxygen. So instead of 5 O2, I have to write 1 O2. And if I have, let me make sure it's not a 10. So it's 1 O2. Let me do it in a different color, because I don't want to think I only have 1 O2 instead of 5 O2s. So how many ammonias are going to react with that? Well, the ratio is 4 to 5. So I'm going to have 0.8 ammonias, right? 4 is to 5 is 0.8 is to 1. And so essentially, if I take this whole equation up here and divide it by 5, I'll get what's actually going to happen. So this divided by 5 is 0.8 nitric oxide, or nitrogen monoxide, plus 6/5 moles of H2O. And so the question was, the original question at the beginning is, how many grams of nitric oxide are we going to produce, or nitrogen monoxide? So how many grams are we going to produce? So we have 1 mole of oxygen, 0.8 moles of ammonia, and we're going to produce 0.8 moles of nitrogen oxide. Or not, sorry, of nitrogen monoxide, right? Because we only have 1 oxygen. So 0.8 moles of nitric oxide, or nitrogen monoxide. So what's the atomic mass, the molecular mass of nitrogen monoxide? Nitrogen is 14, is 14 atomic mass units. Oxygen is 16. All right, we've done that before, but you can confirm here. Oxygen is 16, nitrogen is 14. So 1 molecule of nitrogen monoxide is going to, so 1 molecule of nitrogen monoxide is equal to 30 atomic mass units. 1 mole, or 6.02 times 10 to the 23 molecules of nitrogen oxide, therefore, will be 30 grams. And how many moles are we producing in this reaction? Because oxygen was the limiting reagent. We only had 1 mole of oxygen here. Because of that, we can only produce 0.8 moles of nitrogen monoxide. So 0.8 moles of nitrogen monoxide. 1 mole is 30 grams. So 0.8 moles of NO is going to be equal to 0.8 times 30, which is equal to 24 grams. 24 grams. So we're going to be able to produce 24 grams of nitrogen monoxide. And so you might ask the question, look, we're only using 0.8 moles of ammonia. We were given, in the original problem, we were given 2 moles of ammonia. We were given 2 moles of ammonia. So what happens with all the leftover ammonia? Well, assuming we mix it really good, we're going to literally end up with 1.2 moles of ammonia just doing nothing at the end. So we're going to end up with, so we're going to have 24 grams of nitric oxide, and then we used 0.8 moles of ammonia, and we're going to have left 1.2 moles of ammonia. And if you want, you can figure out how many of the original grams of ammonia that is. You just figure out how many grams 1 mole of ammonia is. It's 17 grams, and then just multiply that times 1.2. Anyway, hope you found that interesting. If you found this a little bit confusing, just watch the video again and pause it and try to solve it yourself. But I think it should start making a little bit of intuitive sense. I think the hard part is just the conversions between moles and grams and getting that part right, and then making sure that you understand the ratios. And you understand, hey, this is a 4 to 5 ratio. There's always going to be less ammonia than oxygen. If I only have 1 mole of oxygen, I'm going to have less than 1 mole of ammonia, even though I was given 2. So oxygen in this example was the rate limiting factor. If I had, let's say I had, I don't know, let's say I had 10 moles of oxygen and 2 moles of ammonia. In that case, ammonia would have been the rate limiting factor, because then I would have had more than enough oxygen. Because for 2 moles of ammonia, I only need 2.5 moles of oxygen. So 10 moles would have been overkill. Anyway, see you